Okay, we will go ahead and get started now. Thanks everyone for joining. We're really excited about today's topic. So first I'll go ahead and give an introduction on our speaker, and then he'll go ahead and go through his presentation, and then at the end we'll have some time for questions if you have time to stick around. Also, this webinar is being recorded, so we will plan to send it out to everybody afterwards, so you can look out for that. So to give a quick introduction on our speaker, Jaren Devey, Mr. Devey has a master's degree in aerospace engineering from Utah State University and is the automotive development lead at Autonomous Solutions Incorporated in Logan, Utah. Prior to his current position, he worked at ASI on the guidance, navigation, and controls team, where he was directly involved in the design and development of the control algorithm referred to as swarming for the choreographed testing of ADAS technology. So yeah, we're really excited to hear from him, and I will go ahead and turn the time over to him.
All right. Sounds good. Yep, like Brooke said, I'm Jaren Devey. I'm the ASI Automotive Development Manager, and really happy to be talking with you about using driverless vehicles to perform ADAS feature critical testing scenarios today. So, what challenges does ADAS testing face? Some of the major problems are as follows. Preliminary testing of ADAS as a whole is only done in simulation. Testing extreme scenarios on real vehicles would not be safe for drivers, nor would they be repeatable with any consistency. Vehicle integration testing solutions include testing only individual components or functionalities. Real-world testing is often done with a safety rider in the vehicle on public roads. This tests some of the functionality of the system, but hopefully would never result in testing of emergency type scenarios. So the problem as we see it is ADAS testing often goes directly from simulation or component/functionality testing to testing on public roads. There's a gap in ensuring that these vehicles are safe for release on public roads. So this presentation will help address that gap. So to answer these problems and be able to accelerate and produce more reliable testing of emerging ADAS technologies, ASI Automotive has developed autonomous systems capable of choreographed vehicle control. We call this swarming. Today, we will discuss what swarming is, why it's needed, and what are the results. In order to be able to present this material adequately, though, a couple of key ASI products and features will also need to be described. So we'll briefly discuss ASI's command and control software Mobius, as well as the ASI robotic system that interfaces with the vehicle. But first, let's just have an overview of swarming. So, no awesome music. You may have seen some of our videos with some really good music, but I'll talk to some of these things here. So the OEM vehicle referred to here as the host vehicle is shown as red in this video. The ASI other controlled vehicles are referred to as target vehicles and are shown as white. This is just an example of the host vehicle sensing the target vehicles while the target vehicles are choreographed around the host. This invokes responses from the ADAS sensors on the OEM vehicle and the different functionalities. So these are real shots of initial testing of swarming with a simulated overview of the test. And so this was one example that we did. The lead vehicle simply just passing in front of the host vehicle or the OEM vehicle. And this would elicit a response. Now this one is one of my favorites. This one I think of as someone missing their exit or about to miss their exit and crosses right in front of you on the highway. I'm sure this has never happened to any of us before. But the scenarios presented in this video are only two of the several dozen scenarios that are already in use, and many of which are running with 5+ vehicles at 65 miles per hour. So according to the levels of driving automation, we are currently testing around the level of L2+. This means that we are still technically in the driver assist realm, but incorporating a whole new layer on top of the traditional ADAS testing features. Most other ADAS testing is done through simulation, but with our solution, you can export paths from your simulator and import them into Mobius to be run on actual vehicles. This will provide you with your desired test atmosphere and the option of higher or lower speeds depending on your scenario. So testing higher levels of automation, L3 through L5, will also experience the same gap that we've already talked about between testing and simulation and being released for testing on public roads. So these levels of automation should be tested using swarming scenarios and vehicles to bridge that gap. Live testing of the complete ADAS platform provides more realistic results than a simulation can produce and is more rigorous than testing individual sensors and components. Swarming scenarios put the test vehicle directly into situations the vehicle could encounter while driving on public roads. With swarming, scenarios can be swapped within seconds, offering a lot more flexibility in testing. This allows for stress testing of ADAS features. Swarming scenarios are often designed with a specific ADAS feature in mind, or can encompass multiple features in a single run. In these scenarios, the ASI robotic system is used to get the host vehicle posed correctly at a defined position and velocity relative to the target vehicles, and then engages and releases control to the OEM's ADAS. The ASI robotic system regains control of the vehicle at a predefined position on the path after the ADAS portion of the scenario. ASI also commands control of the system in case of a failed scenario. The target vehicles utilize the same ASI robotic system to perform their portion of the swarm. So this is an overview of the ASI robotic system hardware. So first we've got our sensors. Sensors collect the environmental information and relay it to the onboard VCU or vehicle control unit to give awareness to the automation system. We are compatible with the Mobileye camera system, but in our swarming scenarios, we don't utilize obstacle detection as it interferes with those extreme test cases. Our control unit, this VCU, is ASI's patented computer. This is the brain of the vehicle. It communicates with sensors and controls the vehicle. It also relays information between the vehicle and the server and ASI's command and control software, which is called Mobius. So the actuators that you see over here, we've got a steering robot and then actuators which interface with the pedals in the vehicle. These universal actuators are placed in the vehicle to communicate with the VCU, the vehicle control unit, so that the vehicle operations can be controlled safely and accurately. In by-wire vehicles, no actuators are needed, as the VCU integrates with the vehicle controls directly. In testing ADAS, it is often more desirable, though, to simulate a human driver rather than using those by-wire capabilities of the vehicle. The ASI system and robots are OEM and vehicle type agnostic, meaning you can use this system in any make and model. The ASI system is also hardware agnostic, meaning that the actuators that we show here are not strictly required, and we can use other actuators from other providers, as well as do the by-wire solution that we already talked about. So these ASI robots are professional drivers. These robots are already used in durability and misuse testing across over 17 OEM proving grounds. They are already taking drivers out of dangerous situations. Swarming is just a natural extension to what these robots are already capable of. Testing ADAS features in any realistic situation requires professional drivers to perform precise and dangerous maneuvers. These ASI robots are the professional drivers needed to ensure that safety and accuracy. So an overview of our ASI Mobius system. This is our command and control software. And so how this works is each vehicle will have that VCU in it, which is part of our overall vehicle automation kit, or VAC. That VAC is installed in the vehicle and then communicates to Mobius. And Mobius is installed on the site network. And then Mobius can communicate with that vehicle and then receives information from the vehicle configuration, like its overall profile and everything. Then Mobius can command the vehicle to go wherever you need it to go. The vehicle will receive those commands, store them locally, and then continue to drive its mission. So this is used already in durability, misuse, and ADAS testing. Now I'll give a brief overview of our swarm scenario design and how that shows up in Mobius, our command and control software. So you can see here that we have several paths that are already defined. All of these paths are part of one swarming scenario. And you can see we show for these paths different things like the velocity profile or the acceleration profile. So all of these things can be previewed beforehand. And these are imported directly from simulations. We also add the ability to be able to engage and disengage the autopilot or the OEM ADAS features as necessary and at specific points, wherever you need them to happen at. We've got here a time lapse of the swarm. And so you can scroll through the swarm scenario and see what's going to happen. For example, here, and we'll just zoom in. You'll see as we go forward in time that the target vehicle 5 is going to pass in front of the host vehicle. And so this is just a regular cut-in with multiple other actors involved. And then as you continue to scroll through time, you'll see that the host vehicle will continue to follow the target vehicle. And this is just a good test of the automatic cruise control, so ACC. Now, what this kind of looks like, and this is just from one of our scenarios, but you can see here that we have these different graphs from actual vehicle performance. And ASI has mainly up to this point been focused on path following and velocity control. But these swarm scenarios are unique in that they require several vehicles be at a specific location and velocity at a given time relative to all other vehicles in the swarm. So this dark green here, you can see in these plots, is the vehicle's actual velocity in meters per second. This light green shows the desired velocity, which is given from the simulation or the swarm scenario. And this blue line here is what we consider as the longitudinal positional error. So if your vehicle is not where it's supposed to be in the longitudinal direction, this is the error to where it should be in time. And so in this specific case here, we show 3 vehicles performing a swarm scenario. The host vehicle was accelerated up to around 29 meters per second. Once it reached a specific point on the path, the ASI robot passed control over to the host's ADAS features. And so that's denoted here by the ADAS engagement point, this red line here. The ADAS ACC speed was targeted for 29 meters per second. The target vehicle 1 then passed in front of the host vehicle while traveling a bit under 27 meters per second. The host ADAS reduced its speed using the ACC to maintain the specific following distance. Target 2 continued to drive in its lane at 29 meters per second. And right before the deceleration phase, the ASI robotic system commanded the ADAS to disengage, which is denoted by this ADAS disengagement red line. And then the ASI system brought all the vehicles to a stop in this swarm. On the safety side of things, a recent study titled Evaluation of Active Driver Assist Systems from May 2022 by AAA Testing multiple L2 ADAS vehicles found safety concerns with ADAS performance and produced a recommendation that, quote, automakers should focus on refining ADA system performance in the context of edge case scenarios involving other passenger vehicles and VRUs. Testing extreme ADAS responses requires multiple extreme test scenarios. These tests are complex and virtually impossible for human drivers to perform. This leads to errors and stress, which can all increase the risk of an incident and possible injury. Not only can the ASI robots perform these extreme tests, but they can repeatedly do so and without fatigue. ASI robots continually monitor the vehicle health data, for example, things like engine temperature, and can stop or prevent a scenario from running in unsafe conditions. Mobius performs pre-planning path checks to only allow valid paths. This ensures there's no chance of a collision even at the maximum allowed error conditions. Removing human drivers from the vehicles makes testing the system safer. When vehicles do fail their scenario, smart stopping is triggered. Smart stopping enables one or more vehicles in a swarm maneuver to activate a safety stop for all the vehicles in the swarm. It utilizes V2V communication to allow vehicles in the swarm to make more intelligent decisions about how they come to a stop when the swarm mission does not go according to plan. Each vehicle receives the position and velocity of all other vehicles collaborating in the swarm. Vehicles can then modulate their velocity to spread out and avoid collision while they're stopping. Each vehicle may modulate its velocity different from other vehicles, which is what sets smart stopping apart from traditional escalated stopping behaviors. ASI's lateral control algorithm utilizes clothoid path following techniques to achieve smooth control. Positional components of the path are sent from Mobius to the VCU. Using an ASI developed EKF, the position of the vehicle is estimated and then compared to the position on the path, and a lateral error is determined. The VCU then determines a steering angle to reduce the error. We refer to this lateral error as off-path error. ASI's longitudinal control algorithm consumes the velocity, distance, and time trajectory from the swarm scenario. Using the aforementioned EKF, the estimated vehicle position is compared to where the vehicle needs to be along the path, and a longitudinal error is determined. We refer to that longitudinal error as the downtrack error. The longitudinal controller then determines the optimal throttle and brake position commands needed to follow the swarm scenario trajectory. When exceeding maximum allowed lateral and longitudinal errors, an escalated stop using smart stopping is triggered. Work is being done to dynamically change these maximum error bounds to account for the planned distance between vehicles in a scenario, rather than having just static maximum values. With each of these vehicles having a robot inside of them, we wanted to determine the consistency of the robots. To view the consistency, we performed 8 runs of the same scenario without expressly changing any variables. We looked at 3 main measurements: the downtrack, the off-path, and velocity error, which is the difference between the actual vehicle velocity and the scenario specified velocity at that specific time. For each of these measurements, we looked at 3 main metrics to compare the results: the average, maximum, and standard deviation. Over the next several plots, you'll see the combination of each of these measurements and metrics with each vehicle represented. The first plot we are looking at shows the average downtrack within each of the 8 runs. Each of the 5 horizontal bar charts represents a vehicle, with the yellow bar chart being the ego or host vehicle. The green dotted horizontal line marks the average across the 8 runs. You can see those here, especially in the top one. The red dotted lines mark the maximum and minimums across the 8 runs. Down in the bottom right of each bar chart is a number showing the standard deviation for this measurement and metric across all 8 runs. Now, these numbers may be a little hard to see or imagine, so I've included some icons for size comparison. This is roughly the height of a person sitting down. The standard deviation icons here show the relative comparison to whichever vehicle has the most standard deviation across the 8 runs, which is, in this case, the ego vehicle with about 0.17 meters of standard deviation. These others show a rough percentage of that maximum standard deviation. From these plots, you can see that the ego vehicle had the largest variance between its runs in how well it matched the scenario positioning. This plot shows the maximum downtrack errors within each of the 8 runs. And so you can see here for size comparison, this is approximately the length of 2 vehicles, bumper to bumper. For each of the non-ego vehicles, these maximum downtrack errors tend to come from the acceleration or deceleration portions of the scenario. For the ego vehicle, though, these maximums come from variations of the vehicle following distance while using the OEM's ACC. We observed that the ego's vehicle performance was not consistent and predictable when using ACC. Each of the robots has biases and tuning considerations associated with it, but performance is very predictable and accurate. One of the main considerations we have to make with tuning of our robots is the engine performance. We have found that the sports car and the truck tend to have more power, which leads to them getting further ahead on their path, while the minivan with less power tends to fall behind a little bit. This plot here shows the standard deviation of the downtrack errors within each of the 8 runs. This helps us determine how consistent the vehicle is within a single run compared to the scenario it is trying to follow. So you can see very consistent between each of the runs with a lot more variation on the ego vehicle or host vehicle. And for another size comparison, this is approximately the length of a single car. Now this plot shows a histogram of all the downtrack data from all 8 runs. This helps us understand the biases in each vehicle and areas we may need to address. It can also be seen that the ego vehicle has a large spread with relatively high downtrack, while the other vehicles tend to have a more narrow band with a lot more focus in the around 0 or slightly biased. And these biases are what I've already talked about, where some vehicles tend to stay ahead behind. Some of this can be accounted for with tuning, but these graphs help us be able to understand that. Now this plot shows the average off-path errors within each of the 8 runs. Now one thing to note here was the convertible was actually traveling on gravel during these paths. So its off-path error or its lateral error was higher than some of the other vehicles. Now the sports car performance indicates to us that we have a bias to the right that needed to be addressed with tuning. The ego vehicle performance shows that it was hardly ever consistent and predictable with its lane following. So for a size comparison, we've added this cup of coffee, about 4 inches tall. And here are the standard deviation plots as well. Now this plot shows the maximum off-path error within each of the 8 runs. These maximums help us determine if there is a high curvature section of the scenario path that we need to specifically consider, like a lane change in the vehicle's tuning. The ego vehicle tended to oscillate during the run within its lane, especially if there was a high curvature section of the road. So for size comparison, this is roughly the size of a 4-year-old child. Now this plot shows the standard deviation of the off-path errors within each of the 8 runs. So again, you can see more variation in the ego vehicle than with the target vehicles. This plot shows histograms of all the off-path data from all 8 runs. And again, you can see a similar trend to what we saw with downtrack data, with a wider spread on the ego vehicle as compared to the other vehicles that were involved in the swarm. This plot shows the average velocity errors within each of the 8 runs. The low magnitudes here, you can see from this wonderful coffee cup comparison again, show that the vehicles all do well with their velocity control. This means that the cruise control portion of the ACC performs well on the ego vehicle, but still has some variations. And with this in mind, you can see that the velocity control on most of the target vehicles performs very well and consistently as well. This plot shows the maximum velocity errors within each of the 8 runs. These maximums tend to come from the acceleration and deceleration stages, which are often outside the times where the ADAS features are used in the scenario. So these maximums, even for the ego vehicle, tend to come from the portion of the scenario where the ASI controller is strictly in control. That's not true for every single case, and there were some of these where the ego vehicle was expressly in control and still achieved a higher velocity error. And this plot shows, as we've seen with the others, the standard deviation of the velocity errors within each of the 8 runs. And the final plot here is, again, a histogram of all the velocity error data from all 8 runs. And so you can see that there was a larger spread with the ego vehicle again, with most of the vehicles still having a good narrow band in their velocity error. Because of data like this, ASI has determined that swarming is highly aligned with the testing of the following and more features of ADAS. Swarming lets you test all these systems simultaneously in real-world scenarios with real-world vehicles. So the adaptive cruise control system that we've already talked about, also forward collision warning, advanced emergency braking systems, blind spot monitoring, adaptive front lighting systems, lane departure warnings, and lane keeping assist systems. Since swarm scenarios are designed to trigger a specific response from the ADAS, the exact expected time of these triggers is known. If the swarm was successful and the expected trigger did not happen, this is a clear indication of a functionality failure of the ADAS component. There are several other features that Mobius and the VCU are capable of performing. I won't get into all of these today, but a couple that I wanted to address are map editing, geofencing, and the robotic safety rider. So map editing is a powerful tool Mobius provides to be able to define the roads and the areas the vehicle needs to stay within. This allows the user to visualize where the swarm scenario will be run. Geofencing is one way that Mobius maps provide safety. Mobius continually monitors the vehicle's position and determines if the vehicle is approaching a map edge. The ASI system will then either slow down, bring to a stop, or bring all swarm vehicles to a stop using smart stopping. The robotic safety rider is a mode in which the ASI system continually monitors the vehicle's condition, such as the position compared to the Mobius map. Even if the ASI system is not in control of the vehicle, the system will then issue a stop command to the vehicle if the map will be or has been breached, or if other conditions have been met, too large of lateral or longitudinal error. This is essentially what the ASI system is doing on the host vehicle while that vehicle is using ADAS. Now, in conclusion here today, swarming is already being used constantly to run ADAS production validation paths at OEM facilities. Customers can test in simulation first, then import these paths into Mobius and run them live on the track. Multiple ADAS features can be tested in a single scenario using several vehicles. Our software controls the OEM vehicle until the test is ready to start, and then seamlessly engages the OEM system and acts as a robotic safety rider. With V2V, smart stopping makes escalated stops much safer. Swarming fills that gap that we talked about between current ADAS testing that uses simulation or other component and functionality validation, and that real-world testing on public roads. So thank you for your attendance today. I really appreciate it and hope that you've been able to glean some information from this. I'd like to open it up for any questions.